Hello everyone. In this video, I'm going to demonstrate a complete installation of Free5G core, which is an open source. We are going to cover a lot of topics as part of this demo. So we'll start with the readiness of the Ubuntu Linux for Free5G core. Then we'll do the installation of the container runtime, where I'm going to install the Docker engine plus Mirantis container runtime. Then we'll move on to the Baremetal installation of the Kubernetes cluster. And finally, we'll complete the Free5G core installation and we'll do the basic UE browsing test. So before we get started with the hands-on demo, let's briefly talk about the 5GS architecture. The 5G core architecture relies primarily on the service-based architecture framework, where the architecture elements are defined in terms of the network functions rather than the traditional network entities. Using SBA framework, any given network function offers its services to all other authorized network functions or to any consumer which can make use of these provided services. In this figure, the lower part network functions provide user plane functionality, while the upper part network functions provide the control plane functionalities. Let's look into some of the important network functions in this 5G core architecture. AMF, which is short for access and mobility function, is an important component of this 5G core architecture. With the functionality of the MME now decomposed, the 5G core access and mobility management function receives all the connection and session related information from the UE over the N1 and N2, but is responsible only for handling the connection and the mobility management task. All the messages related to the session management are now forwarded over the N11 reference interface to the session management function. The next important network function is the SMF, which is short for the session management function. And this handles the calls and the sessions and contacts the UPF accordingly. It manages the user sessions, including the establishment, modification, and release of the sessions, and it can allocate IP addresses for the IP and the PDU sessions. The SMF communicates directly with the UE through the AMF that relays the session related messages between the devices and the SMFs. Now, if we look into the user plane, which is the UPF, it supports the features and the capabilities to facilitate the user plane functions. For example, the packet routing and forwarding, interconnections to the data network, and policy enforcement and data buffering. These are some of the important functions which is catered by the UPF. We have some of the other elements such as the NRF, which is short for the network repository function. It controls the other NFs by providing the support for the network function registration, deregistration, or update services to the NF. It's actually work as a repository of all the network functions. Then we have network functions called UDM, which is short for the Unified Data Management. The functionality is very much similar to what we have for the HSS and HLR in 3G and 4Gs. Then we have a network functions called PCF, which is short for the policy control function. This controls the user data traffic, and it ensures that the user data traffic does not exceed the negotiated bearer capabilities, which has been negotiated between the different network functions. Now, this just provides a very basic overview, high-level overview of this 5GS or 5G core architecture. So now let's move on to the hands-on demo part. So this is my GitHub repo where I have compiled all the steps required to complete this installation and made this repo public. So anybody can access this repo and can follow the steps along. So let's start with the first step of our readiness of the Ubuntu Linux for Free5G core. Let's look into my current setup. So I have deployed an Ubuntu 20.04 6 release, and which comes with the kernel image of 5.15. However, our GTP tunnel module has been compiled on 5.4. Therefore, we are supposed to downgrade this kernel image to 5.4. So let's follow the steps to downgrade this kernel image. It will take a minute or two to have this image downloaded and installed. Now we need to update our grub configuration so we can boot with this new updated kernel. So let's make a copy of our existing grub configuration. Let's modify the grub configuration. Also, let's also install a Linux header generic module as well, which will be required to build our GTB tunnel module. Now let's update the grub. And let's finish the installation of the other required software as well before we reboot the now the next step is to install our Helm, which is a package manager for the Kubernetes. So Helm provides a package management functionality. So we can club all the YAML files into one single package, and we can deploy all the applications and the required dependencies. So we can check if the Helm has been installed. Yep. So now let's reboot the VM. So if you look into our current kernel page, it's still 5.15. So let's reboot and let's wait for the VM to come online again. So now the VM has come online. So let's connect to the VM again. Let's check the kernel image now. So now we can see now our kernel image is 5.4, which is what we require for our GTP kernel module to work correctly. Now let's move on to the next step of installation of container runtime. If you look into the Kubernetes documentation, we have a few options to choose from for the container runtime installation. We have the container D, we have a CRIO, we have a Docker image together with the Mirantis container runtime. So what we are going to do in this demo is we are going to install the Docker engine plus Mirantis container runtime. All the steps are here in this documentation, but just for the ease of the demo, I have compiled all the steps as part of my GitHub repo. So Kubernetes actually requires us to remove the swap partition. So that's why we are going to remove the swap. So let's start with the configuration. Let's move to our now let's check whether the swap has been disabled. Yes. So now there's no more swap. So it's not available anymore. Everything is with a 0 byte. Now let's add the modules. Let's check whether the modules are now available. Yep. Let's set the system parameters. Let's ensure that we can these system parameters are updated values are available without system reboot. And let's verify this value has been set correctly. Yep, so all the values are updated with the 1. So this all seems good. Now let's install the Docker engine. So all these steps are available already on the as part of the Kubernetes, the Docker installation pages. So I'm just following these commands. Let's do the apt update again, and then we will install the Docker. So this will install the Docker engine. just to show you guys. You can just follow along here. Linux. These are all the steps which I am running at the moment. We are here on this step. So this is completed now. So these steps are important when you are running as a non-root user, but we are just going to run this anyway. Let's log out. And let's ensure that Docker is running as expected. So it cannot find the image locally, so it's going to pull this image directly from the Docker Hub. If we look into the Docker image list, this is the latest image which is pulled to run this Docker container. So our Docker is working perfectly fine. Let's ensure that we enable this. So survive the reboot. Now we are going to install the Mirantis container runtime. So let's follow the steps. We're going to get the latest image. We just need to let's move into the local bin. So it's been working fine. Let's download the services and the socket. Let's ensure that we enable this for the boot. Let's check the status. So it's in the active listening state, so all seems good. Similarly, we can check the status for the Docker as well. And the container. So this concludes our second step for the container runtime installation. So now let's move on to the Kubernetes cluster installation. Let's update. Now we are going to install the kubelet, kubeadm and kubectl. And we are going to use the latest release, which should be 1.28. So we can see the release here, 1.28. If we want to install some very specific release, we can actually use the hyphen sign, not the hyphen sign, we can just specifically mention, for example, kubelet equals to the release name, and then it should download the specific image. But in our case, we are going with the latest Kubernetes image, which is 1.28. Now here we are going to use the kubeadm to actually install the Kubernetes cluster. So let's just check the kubeadm version. Sure, everything is fine. Now for our kubeadm initiate, so this will init the cluster, and we are going to use the pod network sider. Should be something different, but we don't have on our network. So we look into the my IP assignment to have two interfaces, ENS33, ENS34, which is at different interfaces, completely different subnet. Then we have the Docker bridge which has been created, and is using a 172.17/16 network. So we need to have the port network sider into a completely different subnet. And runtime, we are going to use the Docker. So now this will create the Kubernetes cluster. It's going to pull the image. So let's wait for this cluster to be created. We can check into the different so you can see it's downloading all these the required component of the Kubernetes cluster: Kube API server, controller manager, scheduler. So once all the component has been downloaded, then it will start the cluster. So it's the kubeproxy has also been downloaded. Let's wait for this cluster to be created. So how quickly these images are downloaded depends on the your network speed as well. So here we have the HCD as well, which was relatively a big image. Oh, now it seems been completing the cluster installation. It's almost completed. Also, as mentioned, all these steps are available here. Alright, so our installation is completed. Now what we need to do is to set the configuration so we can access our cluster. Now if we look into the cluster, so except the core DNS, all the components are in the running state, which is a good sign. Now the core DNS, if you look into the log, is waiting for the container network interface CNI to be available. So let's look into the so it's still in the pending state. Let's install the CNI first. So we have a lot of options for the CNIs. So, but I am going to use the Calico. So We can look into the Calico here if required. Calico installation. So here you can go through these steps as well. So in this case we are going to download the second file. Look into this. So it has installed the Tegera operator which we are going to use. Now let's install the second. We need to modify the custom resource file to align with our port sider. And let's enable the IP forwarding as well. Which is disabled by default. Now let's install this as well. Now this will install the Calico, but it will take a while. So let's wait for the Calico to be completed, installation to be completed. Also we need to install the Multus CNI. So the Multus allows us to install a multiple network on a single port. By default the Kubernetes only allow the port to have a single network, but Multus allows port to have a multiple network. So let's clone the Multus CNI Git repo. Also, just to make our life bit easier, community documentation. Let's go to the cheat sheet. Let's complete this. Okay, let's come out. So let's check the status now. So containers are still being created. So if you remember before, we have the coordinates which were in the pending state. Now they are moved into the container creating stage with the Calico installation completed. look into, we can see all these images being downloaded here. Meanwhile, let's install the Mirantis as well. So most of the container has completed and been running in the perfect status without any restart, except these two Calico API servers which are still in the running state, still in the container creating state, and the Mirantis which is waiting for the CL Calico to be up and running. Meanwhile, let's fix this bash rc file. Let's check. Yeah, so now the Kubernetes cluster is up and running. Everything seems to be in the running state without any restart. This cluster seems very stable at the moment. And it is using the port sider which we actually assigned. So this should conclude our third step for the bare metal deployment of the Kubernetes cluster. Now let's move on to the final step where we are going to deploy our Free5G core. So first of all, we need to build our GTP 5G module. This will be used by the UPF to create the GTP tunnel. Let's clone this GTP 5G repo. So now we are building our GTP 5G module. The next step, been completed successfully. Let's build the module. So let's check whether the module is now available. Yep. So we can see now GTP 5G module is now available. Next, we are going to add the Helm repo for the towards 5G, which actually provides the Helm charts for the free 5G core. Before that, let's create some of the directory structure. Now let's add the repo. To the Helm repo. Now we can see all the charts available with their chart version as well and the app version. We are going to deploy a free 5G core as well as the UE RAN simulator. So let's pull both of them. This will pull the latest release. If you see, we have both the GZ files, and let's create a persistent volume as well. Node name to be replaced with the actual name, which is in our case is Ubuntu. Let's create the required namespaces. So I'm going to deploy these in the different namespaces. For example, I have the user plane, so I'm going to deploy the user plane component, which is the UPF, into the user plane namespace. The rest of the component which is required for the signaling, I'm going to deploy those components into the control plane, which is short for the CP, and into the CP namespace. And then we have the access network namespace. Here I'm going to deploy over my simulator for the UE and the radio network. So I'm going to create these namespaces. And let's create our persistent volume as well. So let's check the persistence has been created correctly. It's now in the available state. Let's create the user plane. Now the Helm install that can be done in a different ways. So we can actually directly modify the value files. So here if you look into the chart, for the Free5G core UPF, we have the values file here. Now why we can directly modify the value files with the required values. For example, here for the master interface, we are going to modify this value to the interface what I have available on my laptop, on my VM. Or we can directly pass this value as an argument during the Helm installation. So in my case, I'm going to pass these values as part of an argument during the Helm install. So if you look into the IP interface, I have the ENS33, which I'm going to use this for the UPF installation. And we need to make sure that the interface, the subnet IP is same what we have for the ENS33. So in my case, the subnet is 10.160.0/24. And then we have the gateway IP as a 10.160.2, which is also the gateway IP here in my case. And I am assigning one free IP from my subnet IP, a subnet range of 10.160.0. This is something we need to make sure that this is configured correctly. So let's deploy this. So let's check the ports. In the user plane namespace. Which is already in the running state. Also we can just now let's check the logs. So we can see the GTP address is running on the 2152 port on this IP. PFCP server has also started, UPF have started, everything seems there's no error logs, seems in a good state. Just log into the port and just make sure that it can access the internet as well. We look into the routing table and then we can check so here you can see all the interfaces, required interfaces has been signed. It has the N3 interface, it has the N6 interface and N4 to connect to the SMF over the PFCP protocol. N6 is your towards the internet and N3 towards the UE, towards the G0B for the user plane to create the GTPU tunnel. Let's try to ping over the N6 interface. So ping is working, but the namespace resolution having some issues. So what we are going to do is we are going to add. So the namespace resolution can be solved in a couple of ways. So what we are going to do, the one method is to actually use the kubedns configuration changes. But here we are going to use a simple resolve.conf. So we are just going to add another namespace here. So it's going to use the default the 888 as a namespace server, and now it's able to ping the google.com as well. This seems up. Let's check whether we have the TCP dump enable open here. Since we don't have the TCP dump, let's update the and install the TCP dump on this pod. Okay, so now we can see the TCP dump is now up and running. Let's enable the ICMP port. Now the user plane is up and running. Now we are going to install the control plane. And for the control plane as well, we are going to use the interface ENS33. So for Free5G core, we have this values.yaml. So we can either modify the values here, or we can directly pass the values as an argument during the Helm install. So let's look into let's add one more tab. Alright, so now it's installing the MongoDB, and then okay, it's also trying to install the UPF. So let's disable the UPF in the value files. So let's uninstall the Helm chart. Let's wait for the Helm chart to be so they are now in the terminating state. So let's wait for them to terminate, and then we'll modify the value file to disable the deployment of the UPF. Since we have already installed the UPF, it will take a while. Right. Okay, most of them is terminated. Meanwhile, look if we have received anything. We are not supposed to. Okay, looks like all gone. Let's delete the namespace as well. Also a good practice to empty our cube data. And let's create the persistent volume again. Right, so let's create the namespace again. Okay, let's check the it's installing now. Let's wait for the containers to be up and running. There is no UPF this time because you have disabled that in the values configuration file. Let's wait for the control plane to be up and running. So if you look into the sequence, first of all the MongoDB comes up, then the NRF, which has the DB Python and the NRF, they comes up. Once the NRF comes up, then the other components, AMF, SMF, UDM, UDR, they all comes online, PCF. So they will be registering all these components, AMF, SMF, PCF, they all have to register with the NRF. Therefore, the NRF the port is coming up first compared to the other ports. Looks like our AMF is also online. Right, seems everything is up. Just wait for a while before we check the log for AMF and the SMF. Right, so now it's the AMF is listening on 38412 on this IP. Everything seems to be in a good state, no error logs, nothing. Similarly, check the SMF as well. So we can see for the PF-CP association request was sent and the UPF has responded back. The accepted response also seems good. No error log. What we need to do is now we need to create the subscriber on our control plane. So we are going to access the web UI. If we look into the services we have for the web UI, which is configured on the node port. So we are going to access this on the port 30500. And what is our node IP? Which is 10.160.102. Right, so the default username and password is admin and Free5G core. Let's create the subscriber. So these are all the default values which are part of the configuration as well. So if you required, you can modify these value and then respectively we need to modify the configuration as well. So I'm going ahead with the default configuration, default values. So here we can see we are going to we have created this UI and we can check these values again here. The PLMN ID, the SUPI, which is the permanent identifier, and compared to the 4G, this is IMSI. In 5G we have something called SUKI as well, which is a concealed identity and been initially used for the authentication. Then we have the SNSSAI parameters as well, which is slice service type and the service differentiator. You have the DNN values, which is nothing but an APN in terms of the 4G. And we have given the QFI and 5QI values in. So now the subscriber is created. So now what we need to do is let's enable the PCAP on the other nodes as well. Let's log into the AMF and the SMF. Let's use the SH. So let's start the trace on the SMF as well. Just make sure it's running fine. right? So we have the user plane trace running on the UPF. We have the TCP dump running on the SMF as well as on the AMF. So let's start the trace. Right. So here we are just capturing the ICMP packets just to make sure that we are receiving the ICMP packet. Okay, let's first of all let's create the UE and radio simulator. Let's check the ports are. So it's creating the container. Let's log into the UE as well. So where's the status? Okay, still in the creating container creating status. Right now it's in the running state. Let's see if we have bash. Yep. Let's see if the gnodeb is in the running, is still in the initializing state. Right, the gnodeb is up. Now you can see the tunnel is up and running. So we can see that now the UE simulator tunnel on the UE port, the user device is up and running. So let's try to ping using this tunnel. So we can ping the Google interface, and let's try to ping directly without the. So we can ping, and now if we check on the UPF, we can see is receiving the packet on the UPF GTP tunnel, and then is sending it to the N6 interface, and then we are getting the response back on the N6, and we are sending the response back on the UPF GTP tunnel. If you check the UE status on the GUI, now you can see that it's in the registered state, it's in the connected state, and so we can see it's in the connected state with the DNN internet. This is the IP which has been assigned, the PDO address. This is an SSCI information, MCC, MNC, and this is the GUTI, 5G GUTI which has been allocated. It's working perfectly fine. Let's first stop our traces here. Let's download the traces. let's download the another EMF as well. Now let's download these on the local disk. Okay, let's move these to the okay, let's change the owner. Okay, now they should be available here. There you go. Let's download on the local laptop. Okay. Let's open the Wireshark. Just a minute, let the Wireshark get started. Let's go to the desktop. Let's check the EMF trace first. Let's check the NGAP. So here you can see this is the initial NG setup request and the setup response. Here you can see the messages what's been passed through. So here you can see this slice support system. So what are the slices are supported, the broadcast, the PLMN ID and the other values as well. And in the response we can see what all the slices been supported over for this AMF. So this is the AMF name, served GUME detail. Here you can see the AMF region ID, set ID pointers, and the relative AMF capacity and the supported PLMN list. In the supported PLMN list, you can see what all the slices are supported, which can be for this particular AMF. Here the initial UE registration request. If you expand this further, you can see all the mobility identity. Here you can see the public key identifier, MSIN, CMNC routing indicator, registration type, which is the initial registration, set as initial registration, and then here you can see all the other parameters related to the UE. Similarly, actually here you can see finally the response being sent. You can take setup request. If you'll see here, okay, so the data is encrypted. We can change this ciphering and we can receive these unencrypted as well. So these are all the values we can check, and the response, and here we can see now if you see into the PDU session establishment accept, further we can see the request, these are the UE MBR values. So here you can see the GTB tunnel ID, and this is the UPF ID. Sorry, not the UPF. I think this is our gnode B ID IP. Similarly, let's open the SMF trace as well. Let's see what's happening in the SMF. So here you can see the SM context, then the PDU session establishment request, this is NES PDU, session management capability SSC mode. So here all the traces, we can look into the traces and we can find out what's really happening right there. So still going on ping. Let's try something different. youtube.com. This is for the youtube.com. So we can see again receiving over the UPF GTP tunnel, sending it to N6, and then getting the response back from the N6, and then sending it back to the UPF GTP tunnel. So ladies and gentlemen, this concludes our demo for the Free5G core installation. So it's now up and running state. So if we look into all our ports, for the control plane ports, we have the AMF, EUSF, NRF, NSSF, PCF, SMF, UDM, UDR installed along with the MongoDB. And on the user plane, we have the UPF, which is actually taking care of the user plane. And on the access network side, we have deployed as a gnode B and the UE. So all these config map which has been actually placed for the respective configuration for the AMF, EUSF, NRF, all the components. Similarly, so if we have to modify anything, we can actually log into and we can modify the configuration. So this is all the values. We can modify the configuration logging into this config manager, and we can update this configuration, but we are not going to do that. Also, there are a lot of IDs available nowadays for the Kubernetes, so we can actually make use of those IDs. Also, if you have to capture the PCAP regularly, I would prefer you to actually download the KubeShark, which is a very powerful tool to take the captures and to analyze the Kubernetes traffic. But it does come with a lot of alright guys, so thank you very much.